Hey everybody. Today we're getting started with areas between curves. We'll go through the basic idea and do a couple of examples. Let's go. To start, let's remember our basic interpretation of the definite integral. Integral from a to b f of x dx means the area under the graph y equals f of x from x equals a to x equals b. We have to remember that that is a signed area, so if the graph of y equals f of x dips below the x-axis, it's going to count as negative area. Here's the picture. In particular, we're thinking of that integral as adding up the areas of infinitely many rectangles, each of which has infinitesimal area. So I like to draw in one of those rectangles. It's going to have width dx and height f of x, and we should imagine one of those rectangles at every single x value between a and b. When we do areas between curves, we have a very similar idea. We draw the two graphs, we find the area between them by adding up the areas of infinitely many rectangles, each of which has infinitesimal width, dx. The height of each of those rectangles at any x value is going to be f of x minus g of x, where f is the greater of the two functions, the one on top. That interpretation gives us this formula. Area between those curves is going to be the integral from a to b, f of x minus g of x dx, where f of x is the graph on top. Let's do a couple of examples. Problem 1. Find the area between the graphs of y equals sine of x over 2 and y equals cosine x over 2 between x equals 0 and x equals pi over 2. I strongly recommend graphing the functions before you start plugging into that formula. If you just start blindly plugging in, you tend to get into trouble. Feel free to use technology to do those graphs. Here we are for these two functions. We can see that the cosine function is going to be on top and the sine function is going to be on the bottom. I've drawn in one of the rectangles. I strongly recommend doing that as well. It helps maintain your intuition as you go through the algebra. In particular, the rectangle should have a width of dx and a height given by the difference between the two functions, top function minus bottom function, cosine of x over 2 minus sine of x over 2. Now we're ready to plug into that formula and do some algebra. Integral from a to b, top curve minus bottom curve, is going to be the integral from 0 to pi over 2. Here we're given the a and b values, the endpoints. The top curve, as we saw in the picture, is cosine of x over 2, and the bottom curve is sine of x over 2. Now we need an antiderivative. We know when we antidifferentiate a cosine, we should get the same sort of sign. When I take that sine of x over 2 and differentiate it, I'll get an unwanted factor of 1/2, so I want to kill that with a factor of 2. Similarly, for negative sine of x over 2, I'm going to get a positive 2 cosine of x over 2. Essentially here, I'm doing that antiderivative by taking a plausible antiderivative, differentiating, and then if I don't get exactly the integrand, I'm fixing it with appropriate constant factors. Okay, so now I need to plug in my limits of integration, 0 and pi over 2. I do that, and then simplify, recognizing that the sine of pi over 4 and the cosine of pi over 4 are both the square root of 2 over 2. Overall, I get 2 root 2 minus 2, about 0.83. Problem 2. Find the area enclosed by the graphs of y equals 3 minus 2x and y equals 6 minus x squared. So in this case, it's even more important to sketch the graphs. The problem doesn't give us any information about where the region begins and where the region ends. So here's the picture. From it, we can see two things. First of all, that the parabola is on top. Y equals 6 minus x squared is higher up than y equals 3 minus 2x. Second of all, the region begins at about x equals negative 1 and ends at about x equals 3. However, we shouldn't assume that those numbers I just said are exact. We actually have to do the algebra. So let's do it. Where these graphs intersect, we're going to have the same x value and the same y value. So I'm going to set the y values equal to get 3 minus 2x equals 6 minus x squared. When I have two polynomials equal to one another, I want to move everything over to one side, so I get the polynomial equal to 0, and then factor. The reason this is helpful is that when I have a product equal to 0, one of the factors has to be equal to 0. So here, either x equals negative 1 or x equals 3. Those are going to be the limits of integration. Now, I already said that the parabola was on top. That's going to be the top curve, and the line is going to be on the bottom. So 3 minus 2x will be the bottom curve. So I'm going to do the integral from -1 to 3, 6 minus x squared minus 3 minus 2x. Notice that I was careful to put in those parentheses. I want the whole top curve, 6 minus x squared, minus the whole bottom curve, 3 minus 2x. Let's actually carry out this integral. First, let's simplify a tiny bit, then get an antiderivative, raising the power by 1, multiplying by the reciprocal of the new power. Then let's plug in the endpoints, 3 and -1, and simplify to get 10 and 2/3. That will be the area enclosed by the graphs of y equals 3 minus 2x and y equals 6 minus x squared. Okay, so in these examples, it was very clear from the pictures which graph was on top and which graph was on bottom. What if that isn't totally the case? Two things to bear in mind. First of all, you can always tell which graph is on top at a specific x value just by plugging that x value into both functions. The larger result will be the higher function. Well, that'll be the top curve. Second of all, suppose you mess up. Suppose you accidentally do the integral of the bottom curve minus the top curve. Then you're going to get a negative answer because you'll be integrating a negative quantity over the entire interval. You can fix that just by taking off the negative sign, by taking the absolute value. That's a fast fix.